So we want to look at how to estimate an irrational using a visual aid. But first, to do that, we need to remember how to use a visual aid for a perfect square root. So here we know the square root of 25 is 5 and the square root of 81 is 9. We can set up a visual to help us think about this. So we can see there are exactly 25 boxes. So the square root of 25 gives us a length from here to here of 5. Same thing here. The sides are 5. We see the same thing is true for the square root of 81. If you make a box that is 9 by 9, you will get 81 squares. And we're not going to count these out for now, but if you do, you'll see that there are 81 squares. So the visual we're using is a square in which the individual squares that make it up are what will be under the root, and the value we get is going to be the square root itself. So now, how do we do this with an irrational number? Say, the square root of 24. And I picked this because we know it's very close to the square root of 25. Perfect square, which is 4 by 4. And we're going to add some additional boxes to this. So we need 24 boxes. So I'm going to add a box here, and a box here, and a box here, and a box here. So now we have 20 boxes. So I need 24. It's 21, 22, 23, and 24. And now we look at how many more boxes will we need to make our final square. And we see that we would need one more box. So here, 4 is our whole number. So we'll put in, this is approximately 4. And now we'll count this outer edge. 1, 2, 3, 4, 5, 6, 7, 8 squares. And it would have had a 9th square. So it would be approximately 4 and 8/9. We can use a calculator to verify this value. So this would be approximately 4.89897. 8/9 would be approximately 4.8 repeating. So you can see that these would actually both round out to 4.9. So this is approximately correct to the nearest tenth. So we look for the next closest square root, which will be 81, which we had right here. So I'm going to duplicate that. I've duplicated our 9 squared block, which represents the square root of 81. But we need something that has 98. So we're going to add squares here till we get to 98. So that's going to be 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98. Oop, I did one too many there. That is 99. I've lost count somewhere. That should be 98. So now we can count just along the edge. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and we would need a total of 19 to fill out that edge. So, when we write our value, this will be 9 and 17 19ths. Let's get one that's not as close to the perfect square that it's resembling. So let's do 71. The square root of 71 is close to 64. So that'd be 8 by 8 square. So we have 64 squares represented here, and we need 71. So we'll write 65, 66, 67, 68, 69, 70, and 71. So that is 71 squares. In order to make the next perfect square, we would need to fill out all of these squares here. So we'll start by counting the squares we have here. 1, 2, 3, 4, 5, 6, 7. And the squares we're missing, there's a total of 17 squares needed to complete that edge. So again, these were 8 originally from here to here. So our whole value is 8. And we have 7 out of 17. So the square root of 71 is approximately 8 and 7/17.